Here in section 4.4, we're going to introduce L'Hopital's rule, which is a pretty important rule in evaluating limits. With that said, we're going to be revisiting those limit type problems we saw back in chapter 2, but now with our derivative rules, we're going to be able to evaluate algebraically some limits that were maybe a little bit more difficult or in fact impossible to consider before. And we'll see that this brings in all of those derivative rules that we learned back in chapter 3. So to start, we're going to be looking, at least initially, at limits of the following form, where we have a limit as x approaches c of some function f over some function g, where f of c and g of c both equal 0. In other words, if we naively substitute into our function and we get the form 0 over 0, we will call this a limit of indeterminate form, specifically form 0 over 0. Throughout this section, we're going to consider other types of indeterminate forms, but at least initially, we're going to focus our attention on the 0 over 0 form. We saw back in chapter 2 that when we had this indeterminate form of 0 over 0, we could not proceed normally. We had to do some sort of algebraic trick or some geometric argument in order to help us evaluate this limit. It wasn't that this limit necessarily does not exist, but rather more investigation was needed. Well, instead of doing the variety of algebraic tricks that we saw back in chapter 2, we're going to tackle this with L'Hopital's rule. Here's the main idea behind it. If we start with our function, f of x divided by our function g of x, and we're operating once again under the assumption that f of c and g of c both equal 0. We'll do a little bit of algebraic trickery here. I will subtract 0 from the top and the bottom. I haven't changed anything. But remember, we're assuming that f of c and g of c both equal 0, which means I can replace both of these zeros with f of c and g of c. From here, I can divide both the numerator and denominator by x minus c. Since I've done the same thing to both the top and the bottom of my fraction, I have not changed anything. And some of the more alert amongst you might say, well, wait a second, what if x equals c? Aren't we doing a division by 0? Well, no, remember in the limit, we only care what's happening near c, not actually at c. So I've not done any sleight of hand here. Now I'm taking the limit of a fraction, so I know that I can split this into the limit of the top and the limit of the bottom. But if we look closely at the limit of the top and the limit of the bottom, well, that's just a derivative. This really gets to the heart of L'Hopital's rule. Through this algebra that we've done here, we're able to rewrite our indeterminate form limit into a relationship involving the derivative, provided, of course, that both of these derivatives exist. So let's see a quick example here of how we can actually employ L'Hopital's rule. Suppose we wanted to determine the limit as x approaches 0 of the following function. Note that if we naively substitute in x equals 0, we get 0 minus the sine of 0 all over 0, or 0 over 0. Again, this does not tell us immediately that this limit does not exist, but rather it is an indeterminate form and more investigation is required. Since this expression here is difficult to manipulate algebraically, we'll instead rely on L'Hopital's rule. And so what we will do here is simply take the derivative of the numerator and the derivative of the denominator separately. Both of these are pretty easy to compute. If we differentiate the top function, we of course get 5 minus 2 cosine 2x, the 2 in front of the cosine coming from our chain rule. And the derivative of the denominator, of course, is just 1. This new limit is easy to evaluate. If we plug 0 in, we no longer get an indeterminate form, and in fact, we get a rather nice value, as cosine of 0 is 1, and so this comes to 5 minus 2, or 3. And so this example really gets to the heart of what we are doing with L'Hopital's rule. Given one of these limits that comes out to one of these indeterminate forms, initially 0 over 0, but we'll consider others later on, we will take the derivative of the numerator, take the derivative of the denominator, and given this new expression, see if we can evaluate that limit and get a real number. We'll see more examples in future videos.